Thank you. Thank you all for coming. We did a sound check earlier, but I'm going to ask everybody to shout at me if I'm not at the mic or I'm too quiet or one of those things. I'm a teacher, so I tend to walk all over the front of the room and wave my arms and shout, and it's going to be a little difficult for me to stand in front of this podium where the mics are. So we'll work on it, and we might have to do that together. So thank you, Lisa, for the introduction, and thank you for inviting me to present here. I speak, like I said, to students on a regular basis as a professor at Sul Ross University, and some of those students are geology majors, and some of them are not geology majors, and so I'm a little bit experienced with talking with mixed groups, and it's one of my personal drives to eliminate jargon in the world also, and to get science communication across the spectrum of people who have different backgrounds. So #SciComm is important to me, and I also request that anybody says, what do you mean by that, if something doesn't sit right. So please help yourself to interrupt me. And so I've been asked to talk about geology in the Big Bend. I was asked to talk about anything, and I decided to talk about the evolution of landscapes. And the reason I did that is because it's so beautiful out here, and we have these ideas of how kind of semi-feeling permanent these landscapes are. We love to see the large vistas, the big skies, and contemplate this area. This is a view to the west from CDRI with Blue Mountain right under my name. And this is a view of CDRI from the south, so that beautiful alluvial valley surrounding the dome. And then some of them are very iconic. This is one of those nice Andy Morgan photos from CDRI. And so again, we tend to think that these are very long-lived landscapes, and we like to kind of contemplate our small place in them. And I'm here to shatter that illusion tonight. So everything is very dynamic and very much in flux. And we'll start with the idea that here, this nice view of Santa Elena Canyon, I'm sure most of you have seen. When Cabeza de Vaca showed up here with his crew about 500 years ago, it probably looked almost identical. Maybe a difference in vegetation a little bit, perhaps a difference in fauna, but I'm a geologist, and so those things tend not to exist for me so much. And then when the people who were contemporaries of the people whose footprints were left at White Sands that were recently discovered with a carbon age of between 21 and 23,000 years ago, it probably also looked the same. Very similar anyway. Again, perhaps just a change in the fauna, a change in the flora. Actually, I shouldn't say perhaps, it would be, because 21,000 years ago was the last glacial maximum, and so we had lakes and we had a much cooler and wetter environment here. But Santa Elena Canyon looked just like it did, I'm pretty sure. Now, if we go back even farther, and you'll see that I've adjusted the timeline. So we've got today on the right, and then the older things that I've been talking about on the left, and it keeps getting compressed because I'm going a little bit farther back in time. And now my really excellent digital artistry skills here have filled in Santa Elena Canyon. So the Rio Grande probably started incising about 3 million years ago. But the thing is, we still had this cliff right there. And so that river found a fracture to go through Mesa de Anguilla, and then it may have taken, roughly this much time to make that canyon the way that we see it today. Let's see. So I want to talk more about deeper time, about longer geologic time. So the front of Mesa de Anguilla there, which has the canyon coming through, is a fault surface. So a fault, we all have this word fault line in our mind. I'd like you to make that go away. It's a surface, not a line, but we have to map a line on the surface of the ground because it's where two surfaces intersect each other. Here's my teacher thing coming through. I'm going to start waving my arms and maybe going away. I'll try not to. So the trace of the Terlingua Fault surface is at the base of Mesa de Anguilla there, right at Santa Elena Canyon. And this is about where I have to stop modifying this one single photo to try to go back in time, because I tried to take the front of the block of rock in front of that Terlingua Fault and move it up. Not so good. So instead, we'll look at a map, which is what geologists use to think and to communicate. And so we have here a map of New Mexico and West Texas, Trans-Pecos, Texas, basically, with cities there in their first initials. So you see Carlsbad, Pecos, Fort Stockton, and then the difference between Texas and Mexico. So there's the river right here. And everything that I've colored in yellow is a basin of the Rio Grande Rift. So this is a down-dropped, linear, focused zone of continental extension, meaning stretching, meaning the continent is stretching. And so in wondering why, I'm going to try to get us all on the same page a little bit with some basic plate tectonics. But before I get to our Tectonics 101, we're going to look at this map on the left of the Western North American plate, that its edge is the San Andreas Fault, which is has this sideways motion where North American plate is moving to the southeast relative to the Pacific plate, which is moving to the northwest. Most of the Pacific plate is ocean crust with a tiny little bit of continental crust. So this belongs to the Pacific plate, and it's moving northwest relative to the rest of North America. But the Pacific plate itself has an absolute motion that's not parallel to that San Andreas Fault. It's moving westward away from that. And so what that does is it pulls that whole plate margin, which is the San Andreas Fault, to the west. And that has the effect of pulling and stretching the North American plate's interior on the western side. So to be very specific, it's experiencing tensile stress in that direction that's parallel to the vector of the Pacific plate's motion. So that's why we have a rift right here. And this whole entire province of basin and range, that is an extensional province also, that we effectively can just think of as a wide rift instead of a focused zone like the Rio Grande Rift is, but they're all related. Okay, so now is the crash course in plate tectonics so that we can all be on the same page. For starters, the Earth is a sphere. Are we good with that? Okay. Okay. So this spherical body in space has layers in its interior, and the outermost layer is called the crust. And most all of the parts of Earth's interior are solid, except for the outer core. We have a solid inner core and a liquid outer core. The mantle is also solid, and of course the crust is solid. We're standing on it right now. And we know all this from seismic data, from earthquake data. So when big earthquakes happen, it basically, that energy that is released travels through the solid planet and ends up on the other side of the planet somewhere, and it gets reflected and refracted on its way. And so people who know complex math like Fourier transforms know how to determine the densities of the material that it's going through. And so we have these layers that we know by density. And then we also have a wide variety of a collection of meteorites that have shown up on Earth that we can say, this is the bulk density of all the rocks in the solar system before the rocky bodies got created. And so we have a very good idea of what Earth's interior is like. So this mantle is solid, like I said, But we call it plastic because it flows. It's very hot and it's under high pressure, and so it can actually flow. And then it flowing moves the parts of the crust and this upper part of the mantle as these tectonic plates. And so Earth's outermost layer is broken into pieces that we call plates, and they are rigid, and they interact with each other at their edges. And so this map on the right is showing our different plate boundaries, like this one here in the northern Pacific, where it goes to the Aleutian Islands in Alaska. So those two black arrows, those two plates are moving toward each other at that location. Here in the East Pacific Rise, the western part of this Nazca plate is also the eastern boundary of the Pacific Plate, and they're moving away from each other, meaning crust is being made right there. And then the third kind is where plates slide past each other. So this is our home plate boundary, the San Andreas Fault. Oops. So I wanted to zoom in a little bit on this figure that was on the past one to indicate that these tectonic plates are either made of oceanic crust or continental crust. And that's one of the things in this science. It's like, oh, thank goodness, there's not more to that. There's not that much complexity to it. Ocean crust is what's made at those divergent plate boundaries. I don't have a figure of it here. And it's thin, it's always thin, and it's always dense. And then the continental crust is thicker, and I don't know the word that's the opposite of dense, so I say fluffy. So it's fluffier than the ocean crust is. And then there's this complication that is really hard for intro students. This upper part of the mantle rides along with these plates also. So basically, you've got the crust and then this other part making up the lithosphere. This is a lithospheric plate, a tectonic plate. And so these are the things that you see in such diagrams as this, that this whole entire plate that is made of ocean crust and lithosphere is moving to the right. This whole entire plate that's made of fluffy, thicker continental crust and lithosphere is moving to the left. The mantle underneath, don't worry about that word, the mantle underneath is more dense. And so even though I said it's solid, I did tell you that it's flowing. It also acts as a fluid, and so the crusts and lithosphere are floating on top of the mantle. And those that are more dense, like the ocean crust, sit lower, and those that are less dense sit higher, just like different densities of wood sitting in water. And so that more dense crust can descend and subduct underneath. That's a jargon word, subduct. So this is a subduction zone where we have two plates converging toward each other, and one of those plates is subducting under the other. One of the implications of this, when we have these situations on Earth's surface, is that we're feeling compressive stress there. And so just like having a wad of silly putty between your hands, if you push horizontally into that, it's going to get thinner or shorter in the horizontal direction and then thicker in the vertical direction. So the crust is responding to that compressive stress at the convergent plate boundary. And so implications of plate tectonics. Number one is that all the good stuff geologically happens at the edges. These are rigid plates, and so they're kind of dull in the interiors. You could think dull, you could also think safe, perhaps. But at the margins, you've got volcanoes, you've got earthquakes, and these green bands are actively uplifting mountains. You see that this one is really not at a plate boundary, and so there's some complexity to the rigidity of this one. And so plate margins are basically where the action is. Here's the figure that shows these side views of our different types of plate margins. So we've got when they move past each other, when they move away from each other, and when they move toward each other. And I might come back to this figure. Okay, so the second implication of plate tectonics is that geography changes over time. So this is where I'm starting to say I'm shattering your illusions of permanence of these beautiful landscapes that we live in, because everything is still moving and is still in flux. So we have our image of today's Earth's surface. These various lines are different kinds of plate boundaries. The dark line with the triangles on it is a convergent boundary where plates are coming together and where one of them is subducting under another one. But we go back in time, 65 million years ago, the Atlantic Ocean was smaller, because what's happening right now is that ocean crust is being made between these continents, and so they're moving apart from each other. You might say they're drifting apart from each other, which is what Alfred Wegener in the early 20th century hypothesized, because simply of the shape of the coastlines. And he was told no by his community, and that was only because we didn't have the data at that time to be able to see the seafloor, the topography of the seafloor that shows very clearly that there's an elevated ridge through the middle. So we go further back in time, and these continents are getting closer together. This one says 135 million years ago, 225 million years ago. So this is Pangaea, and there are parts of this supercontinent, Laurasia and Gondwana, that will be part of the story today, because rocks from the events that shaped Pangaea are exposed in the Big Bend area. So geologists don't tend to use these horizontal number lines. Instead of having old on the left and young on the right, we put old on the bottom and young on the top, and that's because of rocks, because all of these pieces of information are stored in rocks, and older rocks are on the bottom and younger rocks are on the top. So we even bring that into our language. If we're talking about the Cretaceous period, for example, and if we're talking about the late Cretaceous, we might get sloppy and say the top of the Cretaceous. And that's just because we're always thinking about lower, older, and upper as younger. So this figure is a really nice classic visualization of Earth history that Ray Troll made several years ago. And so we've got our ages, deep, deep, deep time, Archean to Proterozoic. But you'll note that we've got numbers on the right-hand side here. And you'll also note, if you have, a little bit of mathematicalness to your mind, then you'll see, well, wait a minute. If the bottom here is 4.6 billion years ago, and this line between the Archean and Proterozoic is 2.5, and then this is 0.5 billion, so 542 million, we're expanding the later part significantly. And that's in some part because this is just better exposed and there's more of it left. But we'll see in this talk that we've got events from the Cenozoic, the Mesozoic, and the Paleozoic era that are exposed in the Trans-Pecos area. So I'm going to go back in time kind of slowly over these events that have occurred here, and then we'll go forward really quickly just so that we get our heads on straight with time moving forward instead of backward. But since I started this story with Cabeza de Vaca and then the White Sands footprints and then the Pleistocene, I have to keep going that way. So that's what I'm doing. Okay, so this Terlingua Fault is part of the Rio Grande Rift, and it's been active for the last 30 million years. So I'm going to put little boxes around the parts of the geologic timescale on the right. And again, coming back to our map, this is the section where we live down in here. So again, there's the river, the border. And this is a map showing this is a map that I made that is of the Big Bend area that I've used for my recent research, which I'll talk about a little bit. And I really wanted to highlight it because the Terlingua Fault is right here. So I darkened it. It doesn't usually stand out that dark on a regular map. And there it is over here also. So it crosses the border Mesa de Anguilla in the state park and into the national park is on the left side of this fault. And then we have the Sierra de Santa Elena down into Mexico. And so this whole side of that Terlingua fault is a basin that we call the Sunken Block, and it's made up of other smaller basins in it. But this, you can see, is what's basically colored yellow in here. And those yellows I thought I erased, but I didn't. So Julius Dash was a professor of geology at Sul Ross State University, and in 1969, he was among the first people to constrain the onset of Rio Grande rifting, of this continental extension, to be at about 30 million years. It's maybe 30 or 32 million years. Oh, and here's another piece of anti-jargon. This capital M, little a, stands for the Latin of mega annums, and so it's the very commonly used shorthand to say million years ago. And so we could also use a capital G-A, that would be giga annums, or a lowercase k-a would be kilo annums, 1,000 years. In my mind, I tend to always say million years ago, even though that's not what it means, but it does mean that. So anyway, you're going to see this a lot, and you're going to get the sense of how geologists are very flip and casual with these large blocks of time. So Julius Dash was looking at some igneous rock intrusions that were oriented in very specific ways that indicate what the state of the stress was in the crust. And so he gave us a very firm, nice onset age of, again, 30 to 32 million years ago. The work that I've been doing recently is showing that when the extension of the crust started, it was pulling to the northeast and southwest, but sometime between 13 and 10 million years ago, it changed direction to be pulling to the northwest southeast. And I have to always say why this matters, because it almost seems like, yeah, okay, it went from this to this. But this is from the movement of tectonic plates, and they're large and they're rigid and they are driven by convection cells in the mantle, and so they don't just move around a lot. So that was a significant thing, to have the direction of stretch in the crust rotate like that. The way that I did that is by looking at fault surfaces that have lineations on them. So again, a fault is a surface, and it was made underground. So right now, this exposed surface of a fault is not how it was formed. It would have had to have been buried and underground in another whole wall of rock on the side where the picture is being taken from right now, for those to move adjacent to each other. And faults are just one of the ways, but really the primary way, that the crust gets deformed as a response to that stress. And so I'm looking at the orientations of these lineations on the fault surfaces to determine what directions the crust was being pulled at the time that those faults moved. And then in addition to that, up close and personal with one of these fault surfaces, there are calcite crystals that grow during the fault motion. And so I can get an age, an isotopic uranium-lead absolute age of that fault movement. So that's how I've constrained the change in timing, or the change in orientation, and put a timing on that. And again, that's not a trivial thing, because tectonic plates are large and they don't change course very easily. So that's the rift. And we're not even scratching the surface, really. The next oldest tectonic event here was this magmatic province. And really, a lot of the landscape that we see from Marfa, not in Marfa, but definitely in Alpine and also in Fort Davis and in much of the park, Studi Butte, etc., is magmatic. And so that means formed from rock that had been melted. So it was formed over one of these subduction zones that was a very long-lived subduction zone. And when this happens, some of the chemical and physical conditions are right to melt the bottom of the lithosphere and the top of the mantle right above this subducting slab of ocean crust. And this is a process that takes millions of years for these diapirs of magma to float up into fractures and find their way to get up through the surface and either sit there and cool and crystallize into an igneous rock, or erupt at the surface and become a volcanic igneous rock. So between 47 and 17 million years is a long time of magma everywhere. And this figure is from a journal that was published for Big Bend Ranch State Park, as a lot of the ones that I'll be using here are. So we're going to use that as a little placeholder of where we are, Big Bend Ranch State Park. So this is a map from a really wonderful book that I forgot to credit on this slide. Oh, I did, but it's in black. The Bureau of Economic Geology of the state of Texas has a book called Texas Through Time. And if you're a geology geek or a fan, then I recommend that, and you can talk to me afterward and I'll remind you of what it is. So this is a map of all of the igneous stuff that was made between 47 and 17 million years. So here's Brewster County, here's Presidio County, so there's the Tri-County line right there. So we have the Paisano caldera, it's 36 million years old. The Chinati caldera is 32 million years old. The Pine Canyon caldera in Big Bend National Park is 32.7. So all of these darker colors are calderas, which are large volcanic eruptions that kind of form in a ring, and then over a very, very large magma chamber, such that a ring is formed after that magma chamber is evacuated, and then a circular bit of land over that magma chamber drops, and so you've got this crater, but the word caldera is the same as a very large crater. And so we've got our famous calderas, some of which are in Texas and some of which are in Mexico. And then we also have just this spread of other volcanic rock. So the Chinati Mountains erupted a tuff of the Mitchell Mesa rhyolite, and that spread a ways. The Davis Mountains erupted other lavas and ash clouds, and they spread a ways. And so there's lots and lots of overlapping igneous material that is really kind of hard to pick out for somebody who just likes the tectonic story like me. But here's a part of the Paisano caldera. Again, that was 36 million years old. A view of the south rim in the Chisos Basin. You can see multiple layers that indicate multiple events of eruption. And so when you start looking at these, that is the kind of thing that you see over and over again. Emery Peak is also part of that caldera, that Pine Canyon caldera. And then we've got Barrios Dome on the way from Alpine to Fort Davis. So this is before you get up onto the mesa. And this here is called a laccolith, which is another kind of intrusion of igneous rock or intrusion of magma. And on my little figure, it's the one down here. So we have a large body of magma. Remember, we're over a subduction zone at that time. And that laccolith is above one little feeder here, and it pushes up the strata that were above that. And those older strata are either sedimentary or previously existing volcanic. And so we can see with the annotation here, these older volcanic layers, the Cross and Trachyte, the Star Mountain rhyolite, and then the Sleeping Lion Formation that have been domed up over this upwelling intrusion. And this is another one of those beautiful CDRI photos. This is from CDRI, from the Weston intrusion, yet another intrusive igneous feature looking at the north side of the Barrios Dome. So that's the same feature from the other side. Of course, going down Pinto Canyon Road, we're in the Chinati caldera, and it's kind of the same thing there. There's just layers and layers, and some of them are intrusive and some of them are volcanic, and so it's hard to pick out all of the details, but people have done that. And then, of course, we have the solitario, which is one of the really cool, unique features that's preserved here. And this is like a laccolith, but it's also like a caldera in that it did drop down the center of it. The intrusion itself is not exposed at the surface, but older rock than the strata that were domed up in this circular blister, basically, are exposed. And this is another one of those from the Big Bend Ranch State Park guidebook that shows like 1, 2, 3, and 4 how the solitario formed. So we had older Cretaceous age rock, and even older than that Paleozoic rock underneath it. And then here comes the magma from below. And so the more that this buoyant material tries to make its way to the surface, it's pushing up the rock above it. And then at some point it erupted. So you're releasing the pressure on it for some reason. You know, maybe the magma is moving and it causes an earthquake. And the earthquake causes a landslide and you've released pressure. That's like one way of that happening, but it's always going to be trying because it's buoyant, and so it's upward moving. And then the caldera collapsed, and this is how it's mapped today. So this sequence is put together. The sequence is put together from what we see today. And this series of cartoons I put in here sort of as a way to allow you all to give me a break in not understanding what all of the different layers are for all of these rocks, because in a magmatic province it's so complex. You've just got one thing erupting, and then you've got another thing intruding, and then you have another thing elsewhere erupting and layering over that, and then you have more things intruding. And so it's hard to pick out individual features like B Mountain in Studi Butte, and also the big sill that's across the street from it. Some of those were intruded underground. Let's see, nothing on this page is showing an intrusion, but any of that magma could just sort of stop and stall in here. But then on the surface, it's all overlapping in kind of a nonsensical way also. So the whole magmatic business was happening between 47 and 17 million years ago. And then we have, and I wanted to show a geologic map, which is by color. So again, remember that geologists think from youngest on the top to oldest on the bottom. And so I won't go through all this right now because we're gonna head off to these in just a minute. But all of that intrusive and volcanic rock, all that rock that was formed from liquid rock over the subduction zone, is in red, or red shades. And so we can see the extent of that, including little tiny features everywhere that locally are very iconic. So before the magmatic province started, because this subduction zone was happening and we're pushing one crust into another, we're also making mountains. And the word orogeny means a mountain building event. And like I said before, the crust is going to be shortened in this direction and thickened in this direction. And so we have elevation changes happening. And this is a picture of one of my classes at Dog Canyon in Big Bend National Park. When you see features like this, that had to have come from horizontal compressive stress. So the crust is contracting or shortening in a horizontal direction. And I could also have put big giant arrows going toward each other. Again, this is just like that wad of silly putty between your fists and your horizontal forearms, where the forearms are representing your tectonic plates. And so you're making the crust in between your arms deform. And that deformation is often found in folds. This is a cross-section that I made for this region, although I did it from the other side, so I just reversed this image. So this fold here is what we're seeing right there. And this is an image that I took by drone with permission to get the imagery of that so I could reinterpret the structures there. So the laramide orogeny is very famous, and it was happening here in the Big Bend area between 75 and 50 million years before present. This is another laramide fold. This is a model that I made of the folds that's happening in front of a thrust fault, and then that thrust front propagating and breaking that fold, and the various kinds of structures that you see in those. It is believed that the laramide deformation happened because that subducting slab flattened at some point. And the more, I said the laramide was famous, the more famous outcrops of laramide are in Colorado and Wyoming and in northern New Mexico. And this was really far from the edge of the plate at that time. And so it's kind of weird to have that kind of deformation that far in. And so the hypothesis that is pretty good is that the slab was buoyant, too buoyant to just stay low. And so it rose and it was still compressing, and so it moved itself further into the interior of the continent. Before that happened, we had an ocean here. And this is where I want to impress upon people that the things that change in geologic time are not just the lateral spatial orientations, not just the geography, like how the maps look, but elevation changes too. Remember, the crust is floating on the mantle. And so we're going to have low times and high times depending on what the horizontal forces are on that crust. So here's a picture of an ammonite fossil from the Hot Springs Trail in Big Bend National Park. And this is from the Cretaceous age. And at that time, I didn't pay for this figure, so this is who it belongs to, Colorado Plateau Geosystems. This is Ron Blakey at Northern Arizona University, and he's basically gathered like all the geologic information that exists to make paleogeographic maps, and they're very specific to times. And so this is telling us what all the data show, which is that there was a marine incursion onto the continent all the way up to the Arctic at this time. And so what I wanted, we've seen and we have heard things about, fossils in the mountains, the ocean must have been there. Well, it was low at that time because the laramide orogeny hadn't started. So we hadn't thickened the crust, which means we hadn't made it taller yet. And also at the same time, it was warm on the climate. There was no ice anywhere, and so sea level was high. So those two things combined gave us the Cretaceous interior seaway, which basically looked like the Bahamas shelf for a very large area. And what we have from that are these thick sequences of limestone all over the Big Bend, and not just at the surface exposed, but deep underground also, and some of our important aquifers are in these limestones. And Cretaceous is green, and so all of the green color in our geologic map is outcrops of Cretaceous rock. But it is older than that volcanic rock, so it's also underneath that. The geologic map is just showing what's right there at the surface, but we can drill wells and we can see what else is under there. And so there's even more green underneath all of this volcanic rock too. Okay, so more of these Colorado Plateau Geosystems map are showing us that the beginning of the laramide orogeny started to thicken the western edge of North America and therefore raise the elevation. And so we're basically starting to drive the water out. Florida does reemerge at about 35 million years, for better or for worse. So the next oldest event, so many things have happened in the Big Bend. So many things have happened everywhere, but they're exposed in the Big Bend, and that's what makes it special, is the Ouachita orogeny. That's how you say that word. The Ouachita mountain building event, was the creation of Pangea. And here's Blaine Hall, friend of me and friend of CDRI, who is giving some field trip to some people, like he always did, with a hand-drawn map that is showing where North America was, South America, and Africa. And these would be coming together at about 300 million years ago to collide and make a high mountain range. So here's a zoom in of that lower map. You can see North America, Africa, South America. And so this boundary here is the range of the mountain that was made from that collision. And so here's a more professionally drafted version. And the Ouachita Mountains, which are in Arkansas, something like that, as well as the Appalachian Mountains. That was part of that same event. So it was basically that Pangea was the suturing or the zipping together of the Laurentian continent and the Gondwanan continent, and these mountains were a result of that. So this is a nice cross-section, again, from that Henry booklet that is showing how these formerly horizontal strata of sedimentary rock got crumpled up just like you're pushing a couch against a rug. And so it's that same horizontal force, and in this case, that thin strata at the top gets deformed perpendicular to that oncoming stress. And this happened around 300 million years ago. So we're in a different era, the Paleozoic era, when this happens. And it was deforming even older rocks. Those older rocks are Ordovician to Pennsylvanian age, so those are the ages or periods within the era of the Paleozoic, and they're colored in these purple shades. And so they're older. You can see that there's not as much of them exposed at the surface. But just like the Cretaceous rocks that are under all the volcanics, all of these purple-colored Ordovician Paleozoic rocks that have been deformed are underneath everything else. So this is the Marathon area. There's Marathon right there. And these rocks are crumpled in this direction that is always northeast to southwest. And that's because that South American continent was coming from the southeast to the northwest. And so that's, again, a response to stress in the crust, and that's what structures give us, is the information about what happened there. So remember that the implication, or one of the implications, is that geography has changed over time. So this is a sequence of maps from that Texas Through Time book from the Bureau of Economic Geology. And it's Texas through time. So there's Texas through this whole thing, which is really convenient to get your bearings. And so from 400 million years ago, remember a million years ago, from 400 million years ago to present, this is what we know from, again, lots of information, whether it's looking at sediments, whether it's looking at igneous rocks, and the shape of the magnetic field that has been frozen in those volcanic rocks, fitting with the time. We can put tectonic plates back together to their positions over time. And so I want to also stress that these horizontal changes, meaning the position of something parallel to Earth's surface, is also going to be accompanied by vertical changes. And now we're going to fast go forward through time. So more happened before the Ouachita orogeny, but it's not exposed at the surface. We could look at geophysical data like magnetic differences in what's red from below and gravity differences in what's red from below. And people do that, and they've got very good maps of the even older rock. But I don't know much about that, so I'm not bringing it into my talk. And also, it's just not exposed at the surface, so it's not part of the landscape except for being the foundation underneath it. So again, the oldest thing that happened here was the Ouachita orogeny. This is when Pangea was created. South America coming in from the southeast to collide with North America and make these like bumps in the strata, like bumps in the rug. More happened, but I'm just focusing on some things. And so the there was a time when those mountains were eroded. So this is much later, at the beginning of the Cretaceous period. So remember that orogeny, that mountain building event, was way back here. So a full 100 million years later is when it was flat again, and also it got warm, and so sea level was high. And this is where we're building limestones through most of Central and Western North America. And then later, from the west came a tectonic plate that's smashing in from the other side. And so this is the laramide orogeny creating these folds. Overlapping with that is this magmatic province. And so this is magma everywhere, and kind of hard to tell the difference between those things. And so this is later, between 47 and 17 million years old. And then this is where the landscape starts to look more like we understand it, where we have cliffs that are the edges of downdropped basins because of the extension that's happening, this continental extension. And you'll remember that the reason that it's extending is because the plate boundary itself is being pulled to the west. And so this is producing tensile stress in the continent. And so I wanted to bring a little bit more of my recent research into this, which is, there's our map of the rift, and the beginning of rifting throughout the whole gash, basically, is what it is, this linear set of basins that's documenting stretch that you would think is just parallel or perpendicular to these basins. Those faults that I showed surfaces of, pictures of the surfaces of, are indicative of the actual directions of movement. And so we've got a timeline from the people who've done those studies in the northern part of the rift in New Mexico. And then Julius Dash documented that northeast extension. And then as time progressed, we've got at 20 million years, we have east-west extension up in the northern part of the rift, and we're still extending to the northeast in the lower part of the rift. And then by 10 million years, all parts of the rift are extending east-west. And then today, the current direction that probably started about 2 million years is this rotation to the northwest. Again, on a slide, this is just a bunch of spinning arrows, but this is reflective of major changes in the tectonic plates, and they don't just they do bump around, but they bump around over millions and hundreds of millions of years. And so that change in direction is pretty significant. And what we are arguing, and these are some other data that don't have ages on them. And so what we have argued, I won't spend too much time on this, is that this San Andreas fault, starting with today, this San Andreas fault didn't start the size that it was, but if we go back in time from today, you see this one says 5 to 2 million years, this one says 10 million years, 20 to 30. So extension in Western North America started at 30 million years. That was at the end of the laramide orogeny, when this one tectonic plate was smashing into the west side of the continent, but it had an edge to it. And on the other side of that plate boundary was the Pacific plate moving to the west-northwest. And so when this edge gets subducted, we're basically now subducting a hole underneath the continent to complete that Farallon slab. And so we're starting to feel the stress of the Pacific plate moving northwest, but its influence can't be that large when it's just a tiny little baby nascent San Andreas fault. And so over time it's growing, and that sphere of influence grows, where the stress field from this motion is able to transmit farther into the interior of this rigid tectonic plate. And so today what we see, where both the northern rift and the southern rift, where I did my work, are matching with the overall stress field that's created by the San Andreas fault. This is a paper that'll come out in the journal Geosphere sometime early next year. And so our region, we've got our old rocks that are just exposed in the Marathon area and the Solitario in the center. We've got the Cretaceous rocks. All these lines are faults and axes of folds, so they're representative of the motion that first was the laramide that was smashing in from the southwest to the northeast, and now is extending first this way and now this way. We've got these other faults. It's all a big mess. Geology at the Crossroads was coined by Blaine Hall, and that's because we have these several different globally significant geologic events that have records in the rocks in this region. When you climb up to the desk on the Sulross campus on Hancock Hill in Alpine, you can look north to see the Davis Mountains area, or you don't see the Davis Mountains from there, but you see some of the outflow from the Davis Mountains eruptive centers. You can look east to see some Cretaceous limestone. You can look, closely. You can look east-southeast to see the Marathon fold belt that was a 300 million year old event, and they're all at similar elevations. So that part truly makes me dizzy sometimes, because you're not only recording things old and then younger and then younger and then younger, but other things are happening. There's buoyancy and there are faults that are dropping parts above and below. And so it's a challenge to put your head around these things. But you just do it little piece by little piece, and then you get a big story eventually. I would also point out that here we are looking at the bottom of the top of Hancock Hill. There's boulders here, so they're not in place. That means that it's eroding, and so this is going to continue to change. It's a high surface that is exposed to the weather, and so it's weathering, and so that's going to wear down, just like all of the other high surfaces are. So if we take things away, I want you to understand that the Big Bend area is special. You all know that because you live here and you like it. But really, geologically, it's quite special because of the overlapping of significant geologic events that are recorded in the rocks here. And also that this landscape that can feel very vast and can feel very permanent, and you can feel very small in it, and that's a lovely feeling. It also is still changing. So there's not like a permanent point of reference there. And that's all I have for you today. Thank you.